In 7a, we're discussing the fundamentals of probability. The main topics we'll discuss are a few definitions used in 7a. We'll discuss notations and examples from 7a. We'll touch on probabilities used in the real world, such as in Powerball and poker. We'll discuss odds and the counting property. Two keywords to point out here. Outcomes are the most basic possible results of observations or experiments. Examples of outcomes include those of tossing a coin. In the case of tossing a coin, an outcome would be that the coin lands on tails. Since when we toss a coin, there are two possible outcomes, then the set of outcomes would be those two possible outcomes, maybe in curly brackets here, heads, comma, tails. When tossing a die, the cube has 6 sides, so the set of outcomes would be the list of those possible outcomes when tossing that die. An event is a combination or collection of outcomes. So an event consists of one or more outcomes which share a common property. When tossing 2 dice, the event of tossing doubles would be the set that contains all of those possible outcomes where I have 2 1s, 2 2s, so both die land on the same number. Outcomes are basic results of observations or experiments, whereas events are a collection of those outcomes which share a common property. In this section, you will be working probability problems in your homework, and sometimes those outcomes are not given to you, and I encourage you to take a moment to draw or imagine the full set of outcomes. It's often very useful. In the next few slides, I will discuss some charts, tables, and tree diagrams, which can be helpful when representing sample spaces. A sample space is simply a collection of the possible outcomes. Here we have a sample space down below representing the possible outcomes for tossing 2 dice. You have a pinkish reddish dice, and that die could land on one of 6 sides, so 1, 2, 3, etc. The greenish or teal die also has 6 sides, so those are shown by rows. Since each dice has 6 sides, 6 times 6 that's why we have 36 outcomes. The sample space is simply the collection of all of those possible outcomes. Now, an event, so notice an event of rolling doubles, those would be all of the possible outcomes that have that in common. I would count those up and you'll see 1 snake eyes here, 2 2s, 3 3s, etc. I have 6 of those. When we represent probability, a common notation we often use is this uppercase P with parentheses around an event, here using the letter E. So this is the probability of an event E. This is how to denote that. The probability of an event will be from 0 to 1 inclusive, where the probability, if the probability of an event is 0, that means there is absolutely no chance that event could occur. If the probability is equal to 1, that means it is absolutely certain that that event will occur. So 1 meaning 100%. Probabilities can be expressed as percentages, fractions, or decimals. So please make sure that you practice those different representations. If I say that the probability of an event is 25%, I could also express that as 1/4, and I could also say that it would be 0.25. Those are all equivalent expressions for probability. Again, those numbers will just range from 0 to 1. 100% is 1. I might have a statement where I use a sentence fragment. So here you might see probability of tossing heads on a coin, or I might abbreviate that. So where H is equal to that event, P of H represents the exact same probability. So probability, we usually use this uppercase P, probability of an event. This is our first notation. There are various methods to calculating probability. Empirical probability would be if I spent time numerous hours actually completing an experiment repeatedly over and over again so that I could count up the number of times I observed a particular event out of the total number of experiments. Now this takes a considerable amount of time, and in some cases it isn't even possible for us to complete probability using empirical probability. But fortunately, in mathematics, more commonly we use theoretical probability. Theoretical probability says that for any event E, the probability of that event is equivalent to the ratio of the total number of ways that a particular event can occur divided by the total possible outcomes. Fortunately, theoretical probability, you might kind of think of that as a shortcut because although it cannot guarantee the outcome of a particular event, we see in mathematics that theoretical and empirical values will approach the same value after numerous trials. So if I were to carry out these experiments for days and days and days, maybe years, eventually those numbers should merge to the theoretical probability. So theoretical probability is what we will focus on in this class as a math class. When we are solving for probabilities, again, it is helpful to use a sample space. So I've pulled up the sample space again here, representing all of the possible outcomes from tossing 2 dice. And we are going to find the probability of rolling doubles. Now you'll recall before we counted up there were 6 outcomes in which the die land on the same number, 36 total outcomes. 6 divided by 36 gives us 1/6. So the probability of rolling doubles would be 1/6. As a percentage, this is approximately 16.67%. The probability of rolling at least 1 1. In order to calculate this, we count up all of the outcomes where we have at least 1 1. Since the pink die could land on 1 in 6 different outcomes, and the teal die also has 1 of 6 sides, so we see 6 here, we have an overlap when we have snake eyes. So totaling all of these together, we have 11 cases. There are 11 possible ways that we can have at least 1 1. So 11 is my numerator, and 36 represents the total possible outcomes. 11 over 36 is the probability of rolling at least 1 1 when tossing 2 die. This is approximately 30.6%. A second notation we need to discuss is that of the probability of an event not occurring. You may see this symbol here, a little elbow right corner of a square here in front of the E. So this represents the probability of an event not occurring. Since the probability of an event not occurring is simply kind of the opposite probability, so it's 100% or 1 minus the probability of that event occurring, then to work an example similar to what we did, since we knew the probability of tossing doubles from 2 dice was about 16.67%, then immediately we know the probability of not tossing doubles would be 100% minus that probability, 16.67. So remember, 100% is simply 1. So 100% minus 16.67% is approximately 83.33%. Tree diagrams are also a useful way to represent a sample space, especially with tossing coins. Since tossing a coin each time, those are independent events, we have a tree diagram here. Tree diagram coming from the name that each of these, you could think of these as branches. So this tree diagram represents all of the possible cases that could result from tossing a coin twice. We want to use this tree diagram in order to find the probability of tossing that coin twice and having that same coin never lands on tails. So the outcomes which will not include tails. Talking you through this tree diagram, you'll notice each vertice represents the toss of the coin. So this first vertice here would be our first event, and it has 2 branches. Those 2 branches represent the possible outcomes. It either lands on heads or tails, and there is a 50% chance for each of those. Depending on that outcome, we will toss the coin again. So if it landed on heads, then the two possible outcomes here, the branches break off again into heads and tails. Each of those have a one of two chance. So here we had tails first, and on the second toss, you could again have heads or tails. There are 4 possible outcomes then from tossing a coin twice. The coin could land on heads twice in a row, tails twice in a row,
or 2 other cases.
In order to solve this probability, we count up the total number of outcomes in which there is not a T. So the only one where there is not a T would be when the coin lands on heads twice in a row. This would be 1 of the 4 total cases. So the probability here is 1/4. We will also discuss cards in this class. So for a standard deck, there are 4 suits in a deck of cards. So clubs, hearts, spades, and diamonds. You'll notice there are 13 types of cards. So if you count from the ace to the king, then we have 13 types, 4 suits. That means that we have 52 cards in a standard deck of cards. We call the Jack, Queen, King the face cards, if you see that in any problems. And ace is sometimes considered to be high and sometimes just treated as a 1. We will use that sample space to solve for a few probabilities related to a deck of cards. The first question is about a king. So what is the probability of dealing a king as the first card from a new deck? Now, the probability of an event here, we need to find the total number of ways that event occurs and divide by the total number of possible outcomes. There are 4 kings in a standard deck, so we could use the numerator 4 for the number of kings. The number of cards would be 52, so 4 divided by 52 is an appropriate answer here. Often, we may need to simplify, since 4 divided by 52 is equivalent to 1 divided by 13. And if you recall, there's 1 king out of the 13 types of cards. So for each suit, 1 out of 13 would represent the king for each suit. So 1 out of 13 is the probability of dealing a king as the first card from a new deck. Number 2 asks for the probability of dealing a spade as the first card from a new deck. Since there are 4 suits, and spades are one of those suits, then there is a 1/4 chance of dealing a spade as the first card. We could also answer 0.25 or 25%. Each of those are equivalent probabilities. The probability of dealing a red card as the first card from a new deck of cards would be 1/2. Half of the cards are red. We could count those up. We would count up all of the red cards, divide by the total number of cards. Half of the deck is red, half of the deck is black. The probability of dealing a red card would be 1/2. The probability of not dealing a red card would be 50%. So this would be 1 minus the probability from number 3. 1 minus 50% would be 50%. The probability of not dealing a red card would be 50%.